The Large Hadron Collider will reopen today after 3 years of being shut down for improvements.
As of this week, it has discovered 3 new particles which could help us learn how our universe was born and what its future looks like.
After years of technological improvements, the legendary atom smasher has returned. The Large Hadron Collider, LHC, is back and smashing particles faster than ever before, thrilling scientists with its enhanced capabilities. Just as the world's largest atom smasher got to work, scientists at the physics lab reported the discovery of 3 new exotic particles that might shed light on the force that holds subatomic particles together. What exactly are these mysterious particles? What does it mean in the context of our understanding of the universe? In this video, we dive into the details of these exotic particles that scientists at CERN had just discovered. The Large Hadron Collider is the world's largest and most powerful particle accelerator, speeding subatomic particles at near light speeds along a 17-mile-long, 27-kilometer loop under Geneva. Since its inception in 2010, the collider has resulted in over 3,000 scientific papers. Now, with significant upgrades, it is primed to reveal new findings, according to team members. It's a magic moment, Fabiola Gianotti, Director General of the European Organisation for Nuclear Research, CERN, said during a press conference after the facility's new science run began. "We just had collisions at an unprecedented energy of 13.6 tera-electron volts, and this opens a new era of exploration at CERN," Gianotti added. Increased energy, more collisions and improved data gathering methods may enable scientists to discover more about the subatomic realm, maybe even surpassing the standard model of particle physics. "We really hope that we're going to collect something like 10 times as much data in this next run as we collected before, so hopefully we can see a whole range of new phenomena," said Chris Parkes, a spokesman for the LHCb experiment, during a conference. LHCb studies the beauty quark, or B quark particle, to explore the differences between matter and its counterpart known as antimatter. Parkes stated that it took 15 years of preparation to get to this point, so actually running the upgraded detector is a really exciting time. And that is exactly what occurred in the first run following the 3-year pause and upgrades. The group behind the Large Hadron Collider Beauty, LHCb, has reported the discovery of 3 new exotic particles. Exotic particles like this have previously been theorized but not detected. The collaboration behind this discovery includes around 1,000 scientists from 20 nations across the world. Professor Parkes leads the collaboration, which includes more than 20 members of faculty and PhD students from the University of Manchester. According to their latest discoveries, the multinational LHCb group has discovered 3 previously unseen particles, a novel type of pentaquark, and the first ever pair of tetraquarks. These new particles are made up of quarks, just like protons or neutrons, the particles that make up the nucleus of the atom, revealed Chris Parkes. However, protons and neutrons are made of 3 quarks, whereas exotic particles are made of 4 or 5 quarks. But what exactly are quarks? Democritus, a Greek philosopher, proposed in the 5th century BC that the world was made up of invisible elements called atoms. By the end of the 19th and early 20th centuries, experimental studies revealed that atoms were made up of smaller particles called electrons, neutrons, and protons. In the 1960s, it was discovered that neutrons and protons were made up of even smaller particles known as quarks, and that the interaction of quarks was linked to one of nature's fundamental forces known as the strong force. The force not only keeps atoms together, but it also plays a role in the interactions of other subatomic particles that make the universe tick. Quarks are elementary particles that may be classified into 6 types: up, down, charm, strange, top, and bottom. They commonly unite in groups of 2s or 3s to generate hadrons, which are made up of protons and neutrons, which make up atomic nuclei. They can, on rare occasions, merge into 4-quark and 5-quark particles known as tetraquarks and pentaquarks. Particles made of quarks are known as hadrons. While some theoretical models depict exotic hadrons as single units of strongly bonded quarks, others envision them as pairs of conventional hadrons loosely bound in a molecule-like structure. Only time and additional research into exotic hadrons will reveal if these particles are one, the other, or both. The majority of exotic hadrons found in the last 2 decades are tetraquarks or pentaquarks, with a charm quark and a charm antiquark, with the remaining 2 or 3 quarks being an up, down, strange, or strange antiquark. However, over the last 2 years, the LHCb has identified a variety of exotic hadrons. The collaboration found a tetraquark composed of 2 charm quarks and 2 charm antiquarks 2 years ago, as well as 2 open charm tetraquarks composed of a charm antiquark, an up quark, a down quark, and a strange antiquark. It also discovered the first double open charm tetraquark with 2 charm quarks and an up and down antiquark last year. The particle is said to have open charm if it includes a charm quark but no antiquark. The LHCb team just reported the discovery of new exotic hadrons. The first kind, discovered through an examination of decays of negatively charged B mesons, is a pentaquark composed of a charm quark and a charm antiquark, as well as an up, a down, and a strange quark. It is the first pentaquark discovered to include a strange quark. The discovery has a statistical significance of 15 standard deviations, much beyond the 5 standard deviations necessary to claim particle detections in particle physics. The second kind is a tetraquark that is twice electrically charged. It's an open charm tetraquark made up of a charm quark, a strange antiquark, an up quark, and a down antiquark, and it was discovered with its neutral counterpart in a study of positively charged and neutral B meson decays. The new tetraquarks, discovered with a statistical significance of 6.5 doubly charged particle and 8 neutral particle standard deviations, are the first pair of tetraquarks discovered. The team also discovered novel methods for these quarks, the smallest particles known to man, to interact with one another. Each is unique, but experts are thrilled about the qualities of the 3 new finds. The new structures exist for just 100,000th of a billionth of a second, but may explain how our universe is formed. The unique pentaquark decays into particles that none of the others make, but the 2 tetraquarks have the same mass, implying that they are the first pair of exotic structures known. Perhaps more crucially, the new discoveries indicate that there are now enough of these particles to start grouping them together, much like the chemical elements in the periodic table. That is an important first step in developing a theory and set of rules for exotic mass. It may appear archaic to work out minuscule variations between the tiniest objects we know about, yet the interaction of quarks provides the so-called strong force that binds the insides of atoms and, by extension, our whole universe together. The strong force is extremely difficult to calculate, and we don't have firm predictions of how the exotic pentaquarks and tetraquarks are built, says Professor Chris Parkes. But we hope that by finding out about them, we can develop theories that enable us to understand them better. While this discovery was unexpected and fascinating, scientists say the dream scenario would be LHC finally revealing the elusive nature of dark matter, which makes up much of the known universe but cannot be seen directly with conventional instruments because accurate measurements of dark matter are critical in predicting the expansion of the universe. With the restart of CERN's Large Hadron Collider, LHC, after a 3-year break, the enormous particle accelerator has a new goal in sight: the search for dark matter, the elusive substance that must account for about 80% of all matter in the universe, but which no one has ever observed. It's hard to believe, but the great majority of matter in the universe is really hidden from our view. This is one of the most mind-boggling facts of our universe. Astronomers believe dark matter exists because they find its gravitational signatures. Dark matter is the unseen cosmic framework that keeps galaxies and galaxy clusters together. We just do not know what it is. Intriguingly, experiments at the Large Hadron Collider on the smallest scales may hold the key to solving one of the largest scale cosmological mysteries of all. A type of particles called as weakly interacting massive particles, or WIMPs for short, was the leading contender for the identification of dark matter 10 years ago. These would be particles with high masses, explaining dark matter's tremendous gravitational attraction, but which would otherwise only interact or couple with other particles weakly. Now, physicists are examining various kinds of exotic theories for dark matter, including exotica such as a quasi-form of radiation called dark radiation with wavelengths extending to several light years, mini black holes, modified gravity, supersymmetric particles, and other types of exotic matter. Despite these new proposals, it is plausible to identify some form of particle as a leading candidate for the identification of dark matter. We think there has to be other particles that we haven't discovered yet, which aren't part of the standard model, but which could make up dark matter, said Victoria Martin, a professor of particle physics at the University of Edinburgh, Scotland. The Higgs boson, discovered 10 years ago by the LHC, might hold the key. The Higgs boson is the mediator of the Higgs field, which is a universe-spanning source of energy from which heavy particles draw their mass by interacting with the Higgs boson. Dark matter, as we know, is incredibly quiet and secretive, interacting with the rest of the cosmos only through gravity. We can't see it otherwise, so finding it is difficult. If it is a WIMP, it must obtain its mass from the same source as other large particles, namely the Higgs field. This brings the Higgs boson to the center of dark matter research, allowing for a probe into the dark world that was previously unthinkable when the LHC was initially turned on 12 years ago. The theory is that dark matter interacts with the Higgs field. We could witness the Higgs boson decay into dark matter in one of the LHC experiments. If the LHC does detect dark matter, it will be the scientific breakthrough of the century. Do you think CERN scientists will be successful in their search for dark matter? Tell us in the comments.